In this video, we will learn how to describe secondary galvanic cells and explain how they can be recharged. You may be familiar with galvanic cells. Galvanic cells are a type of electrochemical cell in which a spontaneous redox reaction occurs, generating a potential difference between the electrodes of two half cells, and this potential difference drives current through the wire. There are two categories of galvanic cell: primary galvanic cells and secondary galvanic cells. A primary galvanic cell follows this definition very closely. Chemical energy is converted to electrical energy. The same occurs in a secondary galvanic cell, but in a secondary galvanic cell, the opposite can also occur. Electrical energy can be converted to chemical energy. We can define a secondary galvanic cell as a type of electrochemical cell that can be run as both a galvanic cell and as an electrolytic cell. Primary galvanic cells are single-use cells. They run flat when all the chemical energy has been converted to electrical energy. Primary cells cannot be recharged. Secondary galvanic cells, however, are rechargeable. Let's focus on secondary galvanic cells. During discharge, they behave as a galvanic cell, and chemical energy is converted to electrical energy. The process of discharging is when a battery powers or supplies electrical current to an external device as it generates electrons through a redox reaction. During charging, also called recharging, a secondary cell behaves as an electrolytic cell. Electrical energy is converted to chemical energy. Recharging is when an external current is applied to reverse discharging and convert electrical energy into chemical energy. During discharge, a cell loses its energy store. And during recharge, it regains its energy store. Let's now look at some examples of secondary galvanic cells. A common example of a secondary galvanic cell is a car battery, also known as a lead-acid accumulator battery. When starting a car, the battery acts as a galvanic cell to give power to the starter motor during ignition. It also powers the car lights and other electrical systems. But whilst driving, the alternator of the car recharges the battery by an electrolytic reaction. So we have galvanic discharge and electrolytic recharge. Another example of a secondary galvanic cell is the rechargeable lithium-ion battery. These types of batteries are used in laptops, smartphones, and in cordless power tools such as a cordless drill. Let's now investigate these two types of batteries, starting with the lead-acid battery. The diagram shows the construction of a lead-acid accumulator battery. Although car batteries differ slightly, most have a similar structure. The anode and cathode are made of plates of lead metal or lead alloys. Each plate is designed like a grid and resemble a waffle, and the grids are filled with special lead materials. The negative anode plates are filled with spongy lead. Spongy lead is a form of finely divided and compressed lead metal, while the positively charged cathode plates are filled with a lead oxide, PbO2, which is lead-4 oxide. Usually there are 6 cells in series, forming a battery with a total cell potential or an EMF of 12 volts. So 2 volts per cell. The cathode and anode plates are immersed in a dilute sulfuric acid electrolyte. The plates are prevented from touching by separators, and the entire system of 6 cells are encased in an insulating material like rubber or plastic. Now that we know the construction of a lead-acid battery, let's have a look at the chemistry which occurs during discharge and recharge. During discharge, that is, while starting the car or running electrical systems such as lights or the radio, the following two half equations occur. At the anode, Spongy lead with an oxidation state of 0 is oxidized to a +2 state. At the cathode, lead 4 is reduced to lead 2. Now these half equations are sometimes written slightly differently, but they all result in the same final or overall reaction equation. Lead from spongy lead reacts with lead 4 oxide and dilute sulfuric acid to produce lead sulfate, which is a solid, and water. The reduction half potential at the anode is negative 0.36 volts, and at the cathode, positive 1.69 volts. Using these values, we can work out the cell potential. Using E cell is equal to E cathode minus E anode. Substituting in these values, we get positive 2.05 volts per cell in the battery. And remember, there are 6 cells, so usually a car battery has an overall cell potential of about 12 volts. We've seen that this overall equation is for discharge. During recharging, the opposite or reverse reaction will occur, and the anode and cathode swap polarity. Over a long period of time, the lead sulfate is not all converted back into the initial reactants. During recharging, over time, the ability of the reverse reaction to occur diminishes. Some of the lead product is converted to a very stable crystalline form, and the amount of lead sulfate available for the reverse reaction decreases. Eventually, batteries need to be recycled or replaced. Now that we know about lead-acid batteries, let's have a look at the lithium-ion battery. We mentioned earlier that lithium-ion batteries are found in many portable electronic devices, for example laptops, mobile phones, and cordless power tools. There are many different types of lithium-ion batteries. The diagram shows a simplified lithium-ion battery. The cathode is composed of lithium cobalt oxide. The anode is made from lithium graphite, where the pink dots in both the anode and cathode represent lithium particles. A plastic separator between the two electrodes separates the two materials, but does allow lithium ions to move through it, hence the name lithium-ion battery. The electrolyte, which coats both electrodes, is lithium hexafluorophosphate. A variety of transition metals can be used depending on the type of lithium-ion battery. This particular lithium-ion battery uses cobalt. When the lithium-ion battery is being used to supply electrical energy to a device, in other words, when it is discharging, the following two half reactions occur. At the anode, oxidation occurs and lithium ions and electrons are liberated. The anode is negatively charged, and electrons entering it flow into the external circuit through the electrical device and into the cathode, which is positively charged. At the same time, liberated lithium ions move through the plastic separator towards the cathode. At the cathode, reduction occurs. Incoming electrons, lithium ions, and the cobalt oxide can react to form the product lithium cobalt oxide. And the overall reaction is LiC6 solid plus CoO2 solid, reacting to give C6 solid plus LiCoO2 solid. A typical lithium-ion battery has an EMF of 3 volts, although voltage varies depending on the type of lithium-ion battery. The reactions shown here represent galvanic action. Remember, the opposite will occur during recharging. Let's have a look. I have erased some information on the screen. Let's now fill in the correct information for a recharging process. This will be electrolytic action, where the battery acts like an electrolytic cell. This time, the anode is the lithium cobalt oxide compound, and the reaction which occurs goes from right to left. Oxidation is still occurring, with LiCoO2 being broken down into cobalt oxide, lithium ions and electrons. The anode now has a positive polarity. Negatively charged electrons enter the anode and leave through the wire and enter the negatively charged cathode. At the same time, lithium ions move from the anode to the cathode through the plastic separator. At the cathode, electrons coming into the wire combine with incoming lithium ions from the anode, and these react with the graphite structure, performing the reverse reaction to reform lithium graphite. Reduction has occurred at the cathode. As a result, the overall reaction will occur from right to left this time. We've learnt a lot about lead-acid batteries and lithium-ion batteries. Now let's compare the two. An advantage of the lead-acid battery is its low internal resistance, which results in it providing high current to the starter motor. However, lead-acid batteries need to be kept upright. This is a disadvantage. They are large and bulky, and they are rather heavy, so they have a low power to weight ratio. Lithium-ion batteries, however, are lightweight, hence their use in many mobile devices. They are relatively small compared to lead-acid batteries, or even very small. They are sealed and so do not need to be kept upright. They provide a large voltage for their size compared to regular alkaline batteries. Incorrect or overcharging of these batteries can shorten the lifespan. Now let's summarize the key points of this video. Secondary galvanic cells can be discharged and recharged. During discharge, they act like a galvanic cell, and during recharge like an electrolytic cell. Lead-acid batteries are an example of a secondary galvanic cell. They are used in cars and consist of spongy lead, which is finely divided lead, and lead-4 oxide electrodes in a sulfuric acid electrolyte. These batteries are relatively heavy and large. The second type of secondary galvanic cell we looked at are the lithium-ion batteries. They are often used in mobile devices such as laptops, cellular phones, and power tools. Lithium graphite and a lithium cobalt oxide are commonly used as electrode materials, and these batteries are generally lightweight, small, and generate a large voltage relative to their size.